Alright guys, so today we're going to talk about vectors in space. So what does that mean? Well, we used to have two coordinates, x and y. Now we're going to have three, x, y, and z. So the way we're going to normally write them, we're going to have our x coordinate here, our y coordinate here, and our z coordinate here. So for example, the point 1, 1, 1, well, little imagination, I suppose, is the 1, 2, 1. You're going to go 1 unit in the x direction. You're going to go 2 units in the y. So you have 1 and 2. That's going to give you a point in the xy plane that is called. So that's xy plane that corresponds to your first two coordinates. And then you're going to have a 1 that you're going to go vertically up, perpendicular to that plane. This plane right here is going to be called the xy plane. And so you're going to be going up perpendicular by 1 unit. So roughly this direction, up by 1. And that point is going to correspond to your point 1, 2, 1. So the positive direction, the y is to the right, positive direction in the x is outwards, and positive direction the z is up. So let's do a few more points. So for example, let's say, so this would be my point 1, 2, 1. Let's do a negative 2, 1, negative 1. I told you I don't have too much imagination, so the numbers are pretty just that. They're just 1 and 2s, I suppose. All right, so we're going to do negative 2 in the x. So I'm going to go here. 1 that was my 1. So this is the 1 distance. I'm going to have 1 in this direction. I'm going to need another distance in over here. I guess my axis should have been a bit longer in the negative direction. So it's going to be my negative 2. Then I'm going to do 1 to the right. So I'm going to be going 1 to the right. That's going to be my negative 2, 1. And then I'm going to do 1 down. Very unfortunate positioning. Let me make it positive just because, well, if I go down, it's going to get down here. I don't want to do that. I'm going to go up by 1. So roughly here. And that would be my point. Negative 2, 1, 1. So that's how you plot points in the three-dimensional space. Why did I call these vectors in space? Because there is a duality between points and vectors, because if you set the tail of your vector at the origin and you put the head of the vector at the point, this negative 2, 1, 1 can be thought of either as a point or as a vector. And usually the difference will only be that whenever we're talking about vectors, we're going to do pointy brackets instead of just parentheses. And then the same thing for this one. I'm going to color in different color because it's getting a little bit messy. I could have put the tail here and go to the point 1 to 1 where I would put the head of the vector. And that then gives me a vector that would be just pointy brackets. So that's the only distinction. So let's think about a few more things we can do. We have planes. Let's write the equation of a plane and see how we can plot it. All right, so let's talk about planes for a minute. So, not airplanes, but planes. So remember, for 2 dimensions, we had the idea of a line in 2 dimensions, or let's call it in R2. And remember, those were usually of the form, in the more general form, ax plus by equals c. And if c was equal to 0, then your line was going to go through the origin, and the slope would have been something like negative a over b. If c happens to not be 0, then you would have had a intercept at c over b. And the same thing kind of happens in R3 or in space. well, I wanted to do in space, but I wanted to call this a plane. So let me erase and write plane there. So plane in R3, that's what I meant to write. And so they're going to be of the form, guess what? AX plus BY plus CZ, so that's third coordinate, equals some D. And as it turns out, if D is 0, this plane will go through the origin, and if D is not equal to 0, then it's not going to go through the origin. But now how do we plot it? Because the way we did back in the day with lines, we basically did the intercepts and then we drew the line. So we kind of can follow the same idea. So we can basically draw lines instead of intercepts. You can draw lines and then that'll give you a plane. So let's go ahead and do that. And then I'm going to show you a few more connections between the vector of the form A, B, C, how that vector relates to this plane. All right, so let's go ahead and firstly look at how you would plot those lines. So let me try to do it here still. I think I have enough space. I don't want to be erasing all the time. I mean, if I have to, I will. But let's say that we have, let's do an example here. Now let's say that we have something of the form x plus y minus z equals to 3. I don't know, something like that. So what happens is, if you were to do z equals 0, what is that? When z is equals to 0, you are at this, with respect to this line, you're at the level z equals 0. That will give you the xy plane. So that would be when z is equal to 0. Okay, so when z is equal to 0, what happens? In z equals to 0, you have x plus y equals 3. So at z equals 0, we have x plus y equals 3. So that is a line that if I just go ahead and plot it, I can do it in the way I did lines. So for example, when x is equal to 0, y is equal to 3. So that gives me one intercept here. X equals 0, and then y equals to 3. So let's do 1, 2, 3. So that's going to give me 1 point. Now, when y is equal to 0, so now on this line, and z also still 0, so when y is equal to 0, x is going to be equal to 3. So 1, 2, 3. So that right there gives me a line. And let me draw my plane in this red. So that's going to give me a line that belongs to the plane. And that would be the curve that I obtain when z is equal to 0. That's going to be called the level curve. So that is the line where my, and of course I don't have to stop there, but I'm going to stop here. I mean, the line continues, right? But that is the line where my plane, whatever I'm going to draw right now, is going to intersect the plane z equals to 0. And now I'm going to look at what happens when x is equal to 0. So when x is equal to 0, I'm here. So traveling the x, I'm here, and I'm going to get the whole plane that is going to be the yz plane. That's going to be just straight up and down. So that plane is going to be the plane, and I'm going to draw not going to draw the next one because it's going to get really ugly. So at x equals to 0, I get that plane, and what happens when x is equal to 0? I get another line. At x equals to 0, I get my line, which is going to be y minus z equals to 3. Now, at this point then, when I'm on this plane, and when z is equal to 0, y is still going to be 3. So I'm at that point. So I'm going to get one more point when when y is equal to 0, I get z equals to negative 3. So I'm going to grab 1, more or less, 2, and 3. So I'm going to have another point, and that plane is going to be going also, this line is also going to be included in that plane. Okay, and you can see that once you set those points, this plane is going to include this line as well. And that tells you then that the plane is going to be going in this overall direction. And sometimes it suffices for us to draw that the plane is going to be going in this direction. Not very satisfying because we would like the entire plane. I mean, you can just continue now that you have a few lines. You can continue to draw it, but since I already drew these lines, I'm going to leave it here because I am at the risk of really making a mess. All right, so let me go ahead and show you the way I prefer to draw planes, which is by finding two vectors that will span the plane, and that's more linear algebraic. That's probably why I prefer it. So I'm going to keep this plane here, this equation, and I'm going to show you how to do it. All right, so I decided to change the name of the video because it's going to be planes in space. I'm going to end up talking a lot about planes. We'll do cylinders and spheres probably in the next one, so yeah, it's okay. That's how it goes. So the way I'm going to deal with this now more linear algebraically is I'm going to solve for x. So I'm going to subtract y and add z on both sides, and I'm going to obtain that equation. And then what I'm going to do is I'm going to write vectors where these guys are going to become parameters. So I'm going to write it in parametric form by, I'm going to allow myself some space here. I'm going to call the equation y equals t and z equals s. And then this x becomes 3 minus t plus s. So this right here become my parametric equations for the plane. Now for a line in R2, remember we had the equations x equals something, a function of t, a linear function of t, and then y, a linear function of t. Well, this didn't have to be linear, but easiest way to express it was with linear functions. However, for a plane, I'm going to have a third equation that is going to give me a z. Now, what that tells me then is that I can choose values for this t and s, and each one of them will give me one vector. So I'm going to grab, and in linear algebra, you do it in a much nicer way, but I'm going to just choose t equals to 0 and s equals to 1, and I'm going to get the vector then. Yes, this notation is completely unnatural to me, but it's okay. So when t is 0 and s is 1, this is going to be 4 for x. Then I'm going to have t equals to 0 and s equals to 1. So I'm going to get one vector here. And then at, I forgot, sorry, I'm going to do it here at t equals to 1, s equals to 0. I'll write it out. Why am I not wanting to write? Let me erase. So at t equals to 1, s equals to 0, you're going to have x, y, z is going to be equal to, now in this case I'm going to have 3 minus 1, so 2. Then I'm going to have 1 and then 0. And the reason why I prefer this method is because it's going to give me two vectors, and when I can draw two vectors, these two vectors generate the entire plane, and that's going to give me a much better idea as to what the plane will look like. So I'm going to draw it still here. I think I can still fit enough of it. A little bit small there, in particular because I need 4. Okay, well, we'll draw it. We'll survive. So for the first one, again, this is going to be x, this is going to be y, and this is going to be z. So I'm going to go 4 units. My units will have to be small. In the x direction, 0 in the y, so I'm done, and 1 up. And now what you have to remember is that these are vectors that I'm drawing. So these vectors are going to be in the plane. So my first vector is going to be this guy here. And my next vector will be 2 in the x, 1, 2, 1 in the y, and 0 in the z. So I'm going to have this vector here. And then what happens is that I can do any combination of these vectors, and that's going to give me a plane. That already tells me more or less where the plane is going to go. So basically I added the two vectors here. And you just continue in this direction. To me, that's a much easier way for the artistically challenged, a much easier way to draw your plane. Does it look much better? I'm not too sure, but at least that to me gives me an idea how to draw it. So I know that the plane goes in this direction, which is kind of the same hand motion I made whenever I gave you that little triangle that determines the entire plane. There went the marker. That determines the entire plane. But I like this one because to me it gives me a very good idea as to, I mean, at least what in linear algebra we call a basis. It's a set of vectors that generate the entire plane. Try to avoid the word span because this is Calc 3, it's not linear algebra. But this is the way I like to do it. There's one more way, and that's going to be based on the fact that if I draw the vector 1, 1 and then -1, so the coefficients here. So if I grab the coefficients here in this equation, and I grab the coefficients and I write them out, they're going to be 1, 1, -1. What is going to happen is if I draw that vector at any point, it's going to be very messy here. That vector is going to be perpendicular to this plane. Do I dare to draw it? I suppose I can. So it's going to be 1, 1. So it's going to be somewhere here, and then -1 down. So the vector that goes in this direction. So if you continue it past the plane, that vector at some point is going to touch the plane and is going to be orthogonal to it. And that is going to be called the normal or the director vector for the, the normal vector to the plane. All right, so let me prove that is true, that whenever you have a plane of the form ax plus bx plus c, z equals 0, that vector is orthogonal. So I'll erase this and I'll be right back. All right, so let's say that you have the plane ax plus by plus c. That looks like an e. Well, it's going to be an e now. Ez equals 0. I'm going to do it for equals 0 because it's much easier. And what is going to happen if you have equals to d, then that vector is just basically going to be a shift, and this still will hold true. You gotta write more in the calculation. Then I'm going to grab the vector n for normal. That is going to be the vector a, b, e. It's annoying to not have to write c. Oh well, it's what it is. So now what I'm going to notice is that any point or any vector, this is it's trivial really, if the vector xyz is on the plane, or the head of the vector, or the point is on the plane, being a little bit careless, right? Because the head of the vector is what is on the plane. Then notice that this vector dot product ABC, well, that is precisely this right here. Oh, I called it C now. E. Easy. Go easy on this. Is going to be equal to 0. And from what we have here, then these two vectors are orthogonal. So the vector ABE is always orthogonal to the plane. And that's one way you can also draw it. So if you have the normal vector, then the plane that is orthogonal to it, that goes through a point, because of course if you have a shift, if this is 0, then it goes through the origin. If you have a shift, then you have to just grab one point. So a plane that is orthogonal to n and goes through a point that satisfies this equation, that is going to be the plane that you're looking for. All right, so there was one more thing I wanted to talk about planes, and that is what happens if you have two planes. How can you determine whether they intersect, and what are the options? What do you have? All right, so let's erase here, and I'll be right back. All right, so if you have the plane AX plus BY plus CZ equals 0. If you've taken linear algebra, you could think about this plane as the null space of the matrix, quote unquote, A, B, C. But now, interestingly, if you have two planes, ax plus by plus cz equals 0, and then you had another one, ex plus fy plus gz equals 0, and you wanted to find if these two planes intersect. Now you're solving a system of equations, which in terms of linear algebra, if you're not familiar with linear algebra, just you would solve this system of equations. That's all I'm saying. But in terms of linear algebra, this would be the null space now of a matrix. So what happens is that this system of equations, you can have the different possibilities. The planes never intersect. That is whenever the system is inconsistent. So if you know linear algebra, it means there's no solutions for this system of equations. So that tells you there's no solutions. And then if there is a solution, notice you will always have a free variable if you're thinking about it in terms of linear algebra. And that means that if there is a solution, then it's going to, these two are going to intersect at a line. And then there's one more possibility, and that is that these two are identical. So the planes are the same. This equation is a multiple of the other. And so you can have no solutions. You can have an infinite solution, meaning a line, or you can have an infinite solution, which is the entire plane where they intersect. But you cannot have just a single point of intersection. So that is just because of the size of the system of equations. So if you have two planes and you want to know if they intersect and where do they intersect, then you would have to solve the system of equations. So say I give you, now I'm going to do x plus y minus z equals 3, same one I had before. And let's say x, oh, am I going to cheat that badly? No, I'm not going to do that. Plus 2y, and then I'm going to do plus z equals to 1, something like that. So you can do elimination, and so you start by eliminating by adding these two equations, and then you get 2x plus 3y is equal to 4. I didn't even help myself by doing something nice, but then I can divide by 2 and I have x plus 3 halves of y. Oh, 3 halves of y, and I put 3 over y. Let me erase. 3 halves of y equals 2. So I can divide by 2, and I can obtain that equation. Now, the only thing that you have here is that you have that the planes are not identical. Why? Because you eliminated z, and so they're not multiples of each other. Because if they were identical, you would eliminate the whole thing, and you would get something of the form 0 equals 0, or 3, or 4 equals 4, or whatever it may be. But you would eliminate everything. So since you eliminated one variable effectively, and you cannot have a single intersection, then this right here is the equation of the line where they intersect. So it's given in general form, and that right there gives you the intersection. Not very exciting, but I think that's about it. I want to talk about